A few days ago, a student asked me about the graph of the gravitational field inside and outside the planet, and it comes up sometimes in the A-level exams, and it's something like this. So outside of the planet, so outside of the radius, it's decreasing with r squared, and inside the planet is a straight line. And the outside part can be reasonable, and we'll see it now because the formula of the gravitational field decreases with r squared, so that's easy. And it's logical that the farther away we are from a planet, the lower the gravitational field. But why is it a straight line when you're inside a planet? Well, let me explain it very easily. So we know the formula of the gravitational field is G equals G m divided by r squared, because remember, it's the force due to gravity on a unit mass. So if we have the force of gravity equals G m divided by r squared, and we consider here a unit mass, so G is only this part over here. So that's a gravitational field. So it decreases with r squared, so it's logical then that when we are at a distance r, when we are at the surface of the planet, at the distance, the radius of the planet, it's its maximum. So for example, in Earth it would be 9.8. And then as we go away, further away from the planet, it tends to 0. So that's logical. But why is it a straight line here? Why is it something like this? The idea is, first of all, to consider it like this, we have to consider that the planet is a sphere and it's got uniform density, okay? So in a sphere of uniform density, if this is r, outside the mass that we have to consider, the capital M, the mass of the planet, is the whole mass of the planet. But as we go into the planet, so if we consider that we're at the distance r1 of the planet, the mass is less than the mass of the whole planet, because we have less planet inside of our radius. And if we consider that the density is uniform, which never happens in a planet really, but it's a theoretical approximation, which makes a bit of sense. The mass equals the density times the volume. So the mass is proportional to the volume. And if we consider this as a sphere, we know that the mass would be density times 4/3 pi r cubed. Okay? So to know what's the gravitational field inside of this green sphere that we have over there, we can substitute in a formula, and instead of m, I'm going to use density times, so that's G density 4/3 pi r cubed divided by r squared. And if and you can see here that the r's can be simplified. R's can be simplified, and we have G density 4/3 pi r, which depends solely on r. It's a straight line. And we can see this much better if we consider that if it had a uniform density, the density is a number which can be obtained by the total mass of the planet divided by 4 pi the radius of the planet cubed. So I've used this formula over here, but in this case I'm calculating the density using the whole planet, because if it's uniform, the density has to be fixed. Okay? So if we substitute that there, we have G equals capital G times m divided by 4/3 by the radius of the sphere of the planet times 4/3 by r. And we can simplify this, and we can obtain a formula that we can see depends solely on r as the variable. So that's, as you see, this part over here is a fixed number, so we can consider it as we can consider it a constant, and so g is that constant times r. So it's a straight line that passes through the origin, and that's the reason why the gravitational field inside a uniform sphere, a planet that's considered a uniform sphere, a sphere with uniform density, is a straight line inside with positive slope, and then here it varies with the inverse of r squared, and here it varies with r. Okay, I hope this solves the problem.